Lisa McPherson here with A Plus College Ready to talk to you here in video 1 about atomic structure. A lot of this might be review, hopefully, so let's get with it, right? Today in video 1 we're going to talk about electromagnetic radiation, the Bohr model of the atom, quantum model, and electron configurations in this video. We start with the electromagnetic spectrum. In this particular diagram, you can see that we have 3 different scales over here. They include frequency on the left in hertz, wavelength here in the center. They have it in centimeters, but mathematically it will always need to be in meters for you. And then over here we have energy of photons in the 3rd scale. Notice the electromagnetic radiation or spectrum covers everything from low frequency, long radio waves, all the way through gamma rays. And so when we talk about electromagnetic radiation, we're not just talking about this narrow band of visible light in here, but we're talking about all types. Okay, now all of these waves have certain properties, and the 2 that we're most concerned with are their wavelength, which is the distance between 2 equidistant or equivalent points on a wave, and then also the frequency, which is how many waves can pass a given point every second. We see here in our last slide that if we look at the numbers for frequency and the numbers for wavelength, we can see that there's an inverse relationship between frequency and wavelength. As the frequency numbers increase, the wavelength numbers will decrease. But between frequency and energy, there's a direct relationship that as frequency increases, the energy increases. So those are good relationships to keep in mind. So mathematically, what we are responsible for are the 2 light equations that show up on the AP Chemistry Equations and Constants page. And the first one is this, where c is the speed of light, lambda is wavelength, and this V-looking letter, which is called nu, the Greek letter nu, represents frequency. In our particular problem here, we are asked what is the frequency, so that's our unknown, and we're given the wavelength at 400 nanometers. So what we're going to do is we're going to algebraically solve this equation for frequency, and that is the speed of light divided by the wavelength. The speed of light is given to you on the equations and constants page, and then the given value here for wavelength is 400 nanometers. Because the speed of light is in meters per second, to get those meters to cancel, our wavelengths are always going to have to be converted to meters if they are not already. So we make this conversion here from nanometers to meters and plug in c and lambda, speed of light divided by the wavelength, and notice the meters cancel, and we are left with frequency expressed in hertz. The frequency, this hertz unit, you can see that what was left over from the calculations right here, that hertz is actually, if we look at it in measurable units, is an inverse second. And that s to the minus 1, it's the same thing as saying 1 divided by seconds. So keep that in mind, that hertz isn't really ever going to cancel itself. It's the inverse second that cancels in our mathematical problems. Okay. So another type of equation that you may have to solve is for energy. So here we're given this question: calculate the energy of a photon of blue light whose wavelength is 450 nanometers. So we're given 450 nanometers, and we want to calculate energy. And so energy is only in this particular equation. Energy is equal to Planck's constant times frequency, but we're not given frequency. But frequency does show up over here in the equation from the other page. So if we solve this for frequency is equal to c over lambda, then we can plug that frequency in over here and get this equation right here, where the energy of the photon is equal to Planck's constant times the speed of light divided by the wavelength. Okay, so now what we're going to do is we're going to plug in h, c, and lambda. H, again, given to you on the equations and constants page. That is Planck's constant. And notice its units joules times seconds. Times the speed of light, again, given to you in the equations and constants page. And then we plug in lambda, but again, we have to convert it. So here's my conversion factor to convert nanometers into meters. And anytime you have problems where you have calculations in units, you need to make sure that the units that you want are the only thing that is left over after you have canceled all other units. So you can see here that nanometers, inverse or seconds, and meters have all canceled, and what we're left with are joules. And since we're solving for energy, to be in joules is something that we should expect. So be really careful with your units. That can cost you valuable points on the AP exam. Okay, so those are the types of calculations that you'll have to do that are based on electromagnetic radiation. But what does that have to do with the atomic structure? Well, let me remind you again of light. So since visible light is what we can see, we're going to be talking about that for a while. And if you take white visible light, like comes out of a light bulb or the sun, and you pass that light through a prism, you will get a continuous spectrum. You'll get this rainbow of colors. If you, however, take a very specific sample of a particular element or a compound, and you excite the electrons for this limited sample, instead of getting a continuous spectrum of light, you're going to get an emission line spectrum where you're going to produce only some specific colors. And then you'll notice that there are these large areas of blackness where those colors of light are not produced. So this is an emission line spectrum in contrast to the continuous spectrum. Now, why is this important? Well, Niels Bohr, who came up with the Bohr model of the atom, did so through his work in spectroscopy. So he was a spectroscopist, and perhaps in your pre-AP class, you were lucky enough to go to lab and look at some of these apparati, like we have over here on the left. If not, maybe you did some flame tests or both. In either case, what you're doing is through electricity or through fire, taking a sample of an element, and in this case we've got hydrogen gas in this tube, and when the electricity is applied, the electrons of the hydrogen atoms get excited to different energy levels, and they give off light. If we take that light and concentrate it and pass it through a prism, instead of getting a continuous spectrum, again, we get this emission spectrum of light. Now, what did that mean to Bohr? Well, when he saw this, he said, wow, hydrogen atoms, when their electrons are excited, they don't produce all energies of light. They only produce these very specific wavelengths, which you can then mathematically convert back into energies. And these specific wavelengths from the emission spectrum, what Bohr did was translate that into his model. Now, how did he do that? We need to remember where light comes from. When an electron is orbiting the nucleus somehow in a lower energy orbit, when we plug it in or catch it on fire or excite it in some way, those electrons can jump out to a higher energy level. They have more energy. But eventually that electron very rapidly is going to drop back down to a lower energy level. Maybe it's ground state, maybe not. But the energy that it gained when it jumped out to the higher energy level has to be conserved. And so that energy gets released from the atom, and it gets released in the form of a photon of light. Now let's look over here at what's called the Balmer series, which is just the visible light emitted, because you can have other types of electromagnetic radiation, UV, infrared, etc., given off by these electrons, but that's not what we see in these emission spectra. So we just want to look at the light we see. So for the hydrogen atom, turns out that if you excite the electrons all the way up to the third energy level, and then they drop down only to the second energy level, that energy difference will produce a particular wavelength of light, 656 nanometers, which turns out to be red light. Now, what if you excite the electron even more? It jumps out to the fourth energy level. When it falls back down to the second energy level, you can see in this diagram that that's a farther distance. That represents more energy. And more energy means higher frequency, but higher frequency means shorter wavelength. So notice the wavelength number has decreased in value. And we've made higher energy light, which we've gone from red to green light. You see this pattern increases as you excite the electrons to higher and higher energy levels. The energy difference between the two n values increases, and as that energy increases, the frequency increases, the wavelength decreases and gets shorter, and that means it's producing different colors of light. And these different colors of light form the emission spectrum. Notice you can only form these colors of light for these transitions. There's no such thing as a n equals 3.5. You can't make that particular energy of light. You can only have these very specific quantized amounts of energy. So what Bohr did was he took those different colors of light and he converted them to different energies and related those to energy levels or distances from the nucleus. So as the energy increases, the energy level gets farther from the nucleus. So you see he translated the line spectrum into energy differences to get these levels. This diagram is a little bit misleading because this shows the energy levels equidistant from each other, and they really aren't. The first energy level is closest to the nucleus, but then there is a large increase of distance between energy level 1 and 2. And then after energy level 2, 2, 3, 4, 5, 6, etc., the energy levels are going to get closer together, and we'll see that in some subsequent diagrams. So remember, this one's a little misleading. Now, the Bohr model is great. We use it, we draw it all the time. It's very user-friendly. It does explain some things, but there are some problems with it. The problem is that it only works really well for hydrogen. And what does works well mean? Well, a model has to agree with the physical data that comes out of experimentation. So the Bohr model does agree well with the spectral data that comes out for the excited hydrogen electron. But for elements like all of them that have more than one electron, multi-electron atoms, these electrons have interactions between each other. They repel each other, and therefore they affect some of these energy calculations that come out of the Bohr model. And so the Bohr model doesn't do a good job for describing any atom other than hydrogen. So clearly that's not terribly useful because that's all the other elements on the periodic table. Also, the Bohr model makes it appear that electrons are traveling in circular orbits. If they were traveling in circular orbits, when they gave off light, they would lose energy. And if they lost energy and lose momentum traveling around the nucleus, because the electrons are negative and the nucleus is positive, as those electrons lose energy, they should fall in. They would have a decaying orbit and eventually fall into the nucleus, and the atom would collapse. And we know that doesn't happen either. So a few problems with the Bohr model. So scientists kept working on this model and looking at the spectra. And so I'm going to introduce you to three guys. Now, disclaimer, for the AP exam, you will not need to know any of these scientists' names, the dates in which they worked. It's not a history test, but it can be helpful to understand the continuum of experimentation and work that was done from one model to the next. So this man, Louis de Broglie, he, amongst other people, came up with this idea and mathematically proved that electrons behave like particles and like waves. They have properties of both, and therefore can mathematically be explained as both particles and waves. So it's known as particle-wave duality of the electron, not just light. This was useful to this man, Erwin Schrödinger. Erwin Schrödinger, who you're probably familiar with as far as his Schrödinger's cat, which is really just a thought experiment and maybe a little entertaining, but not particularly useful for the AP exam. But Erwin Schrödinger, he mathematically took de Broglie's idea and treated the electron, instead of as a particle, mathematically as a standing wave. And he came up with this very complex equation, of which this right here is a condensed form. And in its condensed form, this Greek letter psi is called the wave function. And in the Schrodinger equation, the wave function represents orbitals. Now, orbitals, be careful, are not Bohr orbits. Again, electrons do not travel in orbits, whether they be circular or elliptical, around the nucleus. They've already worked through that math and proven that's not true. So how is it that electrons do travel around the nucleus? Well, there are some limitations to that, but this Schrodinger orbital, or the wave function, is really a probability function. And when you solve that, it gives you these regions around the nucleus where you are 90% likely to find an electron. And so there's regions where of high probability of finding that electron that come from this equation. Those are called orbitals. Now, why don't we know where they are? Well, this guy, Heisenberg, not the guy from Breaking Bad, but this is the original Werner Heisenberg, he came up with the uncertainty principle that says we cannot know both the position and momentum of a particle at a given time. Now, particle in this case very specifically means very tiny particles like electrons, protons, things of that nature. We can tell position and momentum quite easily of things like large things, planets, people, cars, galaxies, ball, a baseball, things like that. But for these small quantum particles, we cannot tell both the position and the momentum of the particle. So because we can't tell both where it is and where it will be later, we can't really tell the exact motion of the electron as it moves around the nucleus. We can just say it's not circular or elliptical as in the Bohr model. So all we can do is make a guesstimate. Well, it's actually better than a guesstimate, but a statistical estimate of where the electron is most likely to be found. Now, how can we imagine that? If we can't imagine electrons traveling around in a specific path like a planet around the sun, this is a pretty good metaphor, this propeller blade. So you can see over here in the picture of this prop plane, we know there are propeller blades, and because of the stop motion photography right here, we can sort of see images of those blades. But in reality, at any given moment, you don't really know exactly where that blade is. What is it that you know? Well, you can tell that the blade is going to be somewhere in this circular region. It's not going to be outside of it. The blade's clearly not going to be out here anywhere. It's going to be in this region someplace. And that's kind of like what an orbital is. If the propeller itself is like the electron moving around the center nucleus, where's the propeller? Where's the electron? Not really sure, but I can tell you there's a really high probability it's somewhere in here. Okay? So that's just a good metaphor or a picture for us to have in our mind of kind of what an orbital is it's that circular area. Okay? Now, not all orbitals come in circles or spheres. The s orbitals do. However, the p orbitals have a different shape. They are called bilobed or dumbbell shaped. In this case, it says peanut. And then we have the d orbitals, and then the f orbitals are even more complex. And you're not going to have to draw these, but I do think it's a good idea to know that at least the s is spherically shaped, and the p orbitals are like these dumbbells or bilobe shapes, or this peanut shape, as they say. So these are orbitals. Now, orbitals are not really like a physical structure around the atom. Again, they're just this kind of statistical area of probability of finding an electron. So if we have a 1s electron or any kind of a s electron, it's going to probably be found in a region around the nucleus in a spherically shaped area or volume. Now, where's the nucleus? The nucleus is where all three, the x, y, and the z axis come together. That vertex represents the nucleus. And notice you can really tell in a p orbital that the orbital comes down to a point of 0, 0, 0 for x, y, and z, where there's really zero chance of finding the electron, and that's at the nucleus. You're not going to expect to find an electron in the nucleus. But out around it, in regions out here, is where you're likely to find it. Not outside it, but inside that colored in region. Now, remember that we have one s orbital 3p equal energy, which are called degenerate orbitals. And that's why over here, like in this Aufbau diagram, you can see that for an s orbital, or s sublevel, there's only one orbital. And for the p sublevels, regardless of the main energy level, the p sublevels have 3 different orbitals, or degenerate equal energy. Notice energy increasing left over here on the left. Equal energy orbitals. And then for the d, we have 5 degenerate, or 5 equal energy orbitals, represented here in this diagram. Now this quantum model gets complicated pretty quickly. So I have included a video here. I'm not going to play here on this video, but you should probably take a look at this at home. Maybe you'll be lucky enough to have a few spare moments in class where you can look at this. And because these orbitals can be very difficult to draw, and complex shapes and things, and it doesn't look anything like we think an atom looks like, it can be really difficult to understand this. I think this video can really help you a lot to kind of make the connection between how we imagine an atom to be, and what these orbital things are, and how they relate to these Aufbau and orbital diagrams. And really it's all about understanding how we express through drawing and writing where we think these electrons are in energy and distance from the nucleus, etc. So take a few minutes and watch this video in your spare time. I think it'll really help you in, as it says, understanding the atom. Now, what is it you're going to have to be able to do that has to do with the quantum model? You don't need to know the historic figures, etc., but what you do need to do are to be able to write electron configurations. So for electron configurations, we've got within a term, we've got these 3 different parts, where the number at first represents the main energy level which an electron is found. Then we have the sublevel, represented by a letter S, P, D, or F. And finally, we have up here, this superscript is the number of electrons in that particular sublevel of that energy level. And remember that the maximum number here for S is 2. The maximum number for P is 6, for D 10, and F 14. So there's 3 different ways they can ask you to write electron configurations, 3 different types. So the first is just to write an electron configuration itself, and it is this type right here that you see. Then they could ask you to write an orbital notation. And orbital notation, however it is, you don't necessarily have to draw boxes. You could just draw blanks above the energy level and sublevel, but it is the one that has the arrows. And remember, when you're filling up these orbitals, you've got to obey Hund's rule, you've got to obey the Aufbau principle and Pauli exclusion principle, and so you have to fill from low to high energy levels, and when you get to degenerate or equal energy orbitals, you have to fill one orbital at a time with electrons in the same spin before you can go back and start pairing them up. So you need to know electron configurations look like this. Orbital diagrams or orbital notation is the one with the arrows. And then the noble gas notation, which is typically used for larger atoms like tellurium we have here, where the electron configurations can get very, very long. And we're usually really wanting to know about the valence shell of the electron, because that's where all the chemical reactivity occurs. And so we shorten this by looking at our element on the periodic table and finding that noble gas that is just smaller than the element we want to write the configuration for, putting that noble gas in brackets, and then all of the elements that are not elements, electrons, that noble gas doesn't have in it, all the way up to the last electron for the element we're writing the configuration for. Those go after that. So we'll take a few minutes to do some practicing here with these 3 types, because you will have to probably do that somewhere on the AP exam. Now, they're not going to give you an Aufbau diagram for order filling, so make sure that you know how to use the periodic table, because you will have that available to you in filling orbitals. Remember that when you get to D sublevel, that the D sublevel N value, or the main energy level value, is 1 less than the period number. So this is period 4, And so the d sublevel electrons are 4, -1, or 3. And when you get to F's, which hopefully they won't put those on the test, but you never know what they're going to do, that the 4 F's here are actually part of period 6. So they are 2 less than their period number. So the 5 F's are actually part of period 7. So 7 minus 2 is 5. Okay, again, some more examples of how we can see how as we move across the period from lithium to beryllium to boron and we add electrons, how does that change the electron configuration and how does that change the orbital diagram or the orbital notation? Be really careful in, remember, these degenerate or equal energy orbitals, we've got to put one electron in at a time with the same spin before we can go back in and start pairing electrons up. So let's take a few minutes to practice a little bit, okay? So here I want you to write the ground state electron configuration for these neutral atoms. We have potassium and neon. So pause the video here, take a few minutes, and write those ground state electron configurations. And then when you replay the video, I will show you the answers. Okay, so the electron configuration for potassium ends in 4s1. Remember that potassium is in period 4. It's in the first square of the s block. For neon, we have it ending in 2s2, 2p6. Remember, all the noble gases except for helium are going to have their s and their p orbitals filled with 2 plus 6 or 8 valence electrons. So the valence electrons show up only in the s and the p sublevels. Okay, now let's try the same thing here with orbital diagram practice. So without me reminding you, I want you to draw a ground state orbital diagram for these neutral atoms. What does that look like? Pause the video and then come back for the answers. Okay, so let's remember what the orbital diagrams look like. Again, you don't have to draw this with the boxes. You can just have a blank, say, with the energy level and the sublevel represented, and then draw the arrows in on top of it. But in any case, anytime that they're asking for orbital diagrams, this is what they want. They want the arrows to be present. Okay, for neon, similarly, we see that all of the orbitals are filled here because this is a noble gas. Now also you may be asked to write electron configurations for ions. And ground state just means, remember, that the lowest energy levels are filled before we go to subsequent higher energy levels. So here we want to do it for ions. Remember, for anions like oxygen, this charge shows that we have 2 more electrons than we would expect. And then for cations, like we have sodium here, we would actually have 1 less electron than we would expect. So pause the video again here, and then come back, and I will show you what the answers are for these 2 ions. So for the oxide ion, we see we have 1s2, 2s2, 2p6, and notice for the sodium ion, it's the same thing. These 2 ions actually have the same electron configuration. These are their most common ions, and they form these ions to have an electron configuration that's more stable, like that of a noble gas, in this case, neon. So these 2 have the same electron configuration, and the term that we use for that is called isoelectronic. The oxide ion and the sodium ion are isoelectronic. Now, another type of ion that you may be asked to draw or write an electron configuration for is a transition metal. And these are a little bit trickier because remember, when you are writing the electron configuration for an ion, you are adding or removing valence electrons, and valence electrons are always in the s and the p sublevels. But for transition metals, their electron configurations don't end in S and P like oxygen and sodium did. They end in D sublevel electrons. So when ions are formed, we are going to be losing valence electrons, which are not going to be in the d sublevel. Instead, we're going to have to take our electrons off, or we're going to add them in the s and p sublevels. So let's take a look at, for transition metals, they're always going to form cations, so they're always going to be losing electrons. So if we take a look at iron here, this is the electron configuration for a neutral iron atom. Now, iron comes in two common oxidation states, a +2 and a +3. So whenever we form the iron ions, we're going to remove their highest energy level valence electrons first, and they're not the 3Ds. Instead, they're the 4S's right there. There's the highest energy level or highest N level. So those are the first two to go. So when we form this iron 2+ ion, now that is really annoying, those tools down there. The iron 2+ ion is everything that we see in the iron atom, but just take away those 4s2 electrons. Now, what if we want to form the iron 3 ion? The iron 3 ion has not only the two 4s electrons removed, but it's also got the third electron coming from the next highest energy level, which is not valence per se. It's not an S or a P, but this is where we're going to start removing the D sublevel electrons. And so we get this configuration for the iron 3 atom, or I'm sorry, ion. So I want you to practice both electron configurations for a neutral atom and then follow that with writing the electron configuration for the transition metal ion after it. So here we've got zinc ion, and molybdenum, and a molybdenum 5+. Molybdenum comes in lots of different oxidation states, but we're just going to focus on the 5+ here. So again, pause the video, come back, and we will look at the answers together. So let's take a look at zinc. Zinc ends in 4s2 3d10. If we're going to form the zinc 2+ ion, what are we going to take off? Well, we're going to take those 4s2 electrons off and end up with this electron configuration instead for the zinc ion. For molybdenum, it's a little bit trickier. So we've got a longer electron configuration here. Notice it ends in 5s2 4d4, and we want to make a 5+ ion. So what are we going to take off first? Well, you're going to find the highest N value, highest energy level value electrons. Those are your valence electrons, and take those off first. But that would just make an MO2+ ion. We need to remove 3 more electrons. Where are those other 3 going to come from? The next sublevel down in energy is going to be 4D, and we're going to remove the next 3 from there, and that's going to result in this electron configuration. It ends in the 4p6 4d1. So all of these that we're practicing on are things that you may be asked to actually draw or write on the AP exam. Now, as far as noble gas electron configurations go, you probably did this in pre-AP. This has been mostly reviewed at this point. You can watch this short video, and it's going to go through some examples of how to take a longer electron configuration and write it out in the shorthand noble gas electron configuration. So I'll let you do that on your own time. Now, the last thing that we got in this video is, again, I'm going to go back and mention what the term isoelectronic means, because they may, in a question, just ask you which of these elements or ions are isoelectronic. You need to know what that means. And it means that these particular elements or ions, once they've been turned into ions and their electron configurations have been changed like we changed them before, notice in their atomic neutral states, they have different electron configurations. But now, once we form these ions, every single one of these elements has the same electron configuration, and that's what isoelectronic means. So you may have to write what the isoelectronic electron configuration is, or more likely to determine which set of elements and ions have are isoelectronic. You need to know what that means before you can answer the question. Okay, so this is the end of video 1, and we will take a look at video 2, which will be on spectroscopy.